Welcome to the Discrete Universe podcast.
Great to be here.
Today, we're doing a deep dive into quantum geometry dynamics, QGD for short. It's a fundamentally different way to look at physics.
It really is a complete rethinking from the ground up, almost.
And for you, the learner, we're tackling a really interesting question. Are there recent observations, especially in cosmology, that might actually, support this QGD framework?
Yeah, that's the crucial question. Does it match what we're seeing out there?
We've got some fascinating sources lined up, stuff about early galaxy formation, how they got so big so fast.
Right, the JWST findings, for instance.
Exactly. And the latest results from DSI, the Dark Energy Spectroscopic Instrument. Plus, we'll touch on the core QGD ideas from Daniel Bernstein.
So the mission today is to unpack these recent findings and see, well, do they fit? Do they maybe even favor QGD over standard models in some cases?
Let's find out. It's definitely a good time to look at alternatives like QGD, isn't it? With all the puzzles and, frankly, tensions in standard cosmology.
Absolutely. Things like the Hubble tension, the early galaxy puzzle, they open the door to considering new fundamental ideas.
So before we dive into the observations, let's quickly lay out the core ideas of QGD. What are we starting with?
Okay, so QGD is axiomatic. It starts with fundamental assumptions. The big one is that space itself isn't smooth and continuous like in general relativity.
It's discrete.
Exactly, discrete. Think of it like it's made of fundamental units, a quantum geometrical structure.
Okay, so space is built from something. What about matter?
All visible matter in QGD is ultimately composed of fundamental dark preons. These have a positive charge designation, so we call them preons plus Beck.
Like creons, so they're not directly visible.
Correct. They're the basic building blocks. And the idea is that when these preons plus interact, convert, they form the more massive particles we actually observe, electrons, quarks, the whole zoo.
Interesting. And the units of space?
Those are the preons. They have a negative charge designation. And here's a major twist. QGD says there's a fundamental repulsive force between these space units. It's called n-gravity.
Repulsive gravity between the bits of space itself.
Precisely. And the force between any two specific preons is always the same fundamental unit, g, a constant base repulsion.
But wait, does that mean space is constantly trying to fly apart uniformly?
It's more subtle. The interaction strength isn't constant with the distance. It actually increases based on the quantum geometrical distance, d, between preons.
How does it increase?
The formula is d squared plus d divided by 2 times that base unit, g. So the further apart the space units, the stronger the repulsion becomes, and it ramps up fast, like quadratically.
Okay, so space pushes itself apart more strongly at larger distances.
Yeah.
What about attraction? We need things to clump together.
Right, that's where p-gravity comes in. That's the attractive force. And it acts between the matter preons, the preons plus...
Okay, so preons plus pull together, preons push apart, and the pushing gets stronger with distance. A cosmic push and pull.
That's the essence of it, a fundamental duality of forces built into the structure of matter and space.
All right, let's connect this to the sky. Those supermassive galaxies in the early universe. They formed way faster than our standard models seem to allow sometimes. How could QGD explain that?
This is potentially a really strong point for QGD. Standard cosmology struggles a bit with forming such massive structures so early, within the first billion years.
Yeah, it seems like there wasn't enough time.
QGD's picture of the early universe is different. It starts with an isotropic state. These free preons, plus, are spread out fairly evenly, but key gravity, the attraction between them, immediately starts pulling them together.
Okay, standard gravity does that too. What's the QGD difference that speeds things up?
It's how gravity behaves in regions that become slightly denser. Because space itself is made of these preons, and matter is preons, plus, the gravitational interactions are inherently tied to these discrete units. In QGD, if you get a slightly denser region of preons, plus, the attractive preons effectively get stronger in that local region. It pulls in more preons, plus, creating a feedback loop. It's like gravity amplifies itself in denser areas, leading to much faster condensation and structure formation than you'd get otherwise.
So it's not just gravity acting on matter, but the distribution of matter fundamentally influences the strength of gravity locally in a way that accelerates clumping.
Exactly. The non-homogeneous distribution leads to heterogeneous gravitational interactions. That inherent amplification could be the key to building those early giants so quickly.
That is a fascinating mechanism. Okay, let's shift focus to the other end of the cosmic scale, dark energy and the universe's expansion. De-ice results are strengthening hints that dark energy might not be constant. It might evolve.
Yes, the latest DSI data suggests the equation of state for dark energy in WBR might not be exactly -1 and might be changing over time. That's hard to explain if dark energy is just Einstein's cosmological constant.
So how does QGD approach this? Does it even need dark energy?
Well, not in the sense of a separate, mysterious energy field filling space. QGD proposes that the effects we attribute to dark energy are actually caused by that repulsive ingravity we talked about.
The push between the space preons.
Yes, but it's scale dependent. Below a certain critical distance, which QGD calls lambda, pronounced anda.
A lambda, got it.
Below lambda, the attractive p-gravity between matter dominates. It holds galaxies together, galaxy clusters together, standard gravity, basically, at those scales.
But beyond lambda.
Beyond a lambda, where the quantum geometrical distance gets large enough, specifically where d squared plus d equals some fundamental constant k in the theory, the net gravitational effect flips. It becomes repulsive.
The end gravity takes over.
Effectively, yes. And remember, that repulsive force increases proportionally to the square of the distance.
Which means the acceleration outward would increase linearly with distance.
Precisely. Which looks remarkably like the accelerating expansion we observe, where more distant galaxies recede faster.
So QGD says no need for a separate dark energy fluid. The acceleration is just gravity doing its thing, but flipping to repulsive mode at cosmic distances.
That's the proposal. It's an inherent property of the quantum geometry of space itself. And if the DSI results hold up and show dark energy evolving,
Yeah?
well, in QGD, the conditions determining d lambda, or that constant k, could potentially be linked to the overall density and distribution of preons in the universe, which has evolved over cosmic time. So QGD might naturally accommodate an evolving acceleration effect.
That's elegant. Potentially, using the same fundamental forces to explain structure formation and cosmic acceleration.
It offers a unified picture, yes.
Okay, another puzzle. Satellite galaxies. Especially around Andromeda, our neighbor. Observations show they're not randomly scattered. They seem to be in, like, planes or streams. Lopsided?
Yes, the planes of satellites problem. It's a persistent tension with simulations based on the standard Lambda Cold Dark Matter, ΛCDM model.
Lambda CDM predicts more of a random sort of spherical swarm, right? Governed by the big dark matter halo.
Generally, yes. While substructure exists, these highly flattened, co-rotating planes observed around Andromeda and maybe even our Milky Way are, let's say, statistically unlikely in many standard simulations.
We've got that figure, too, from one of the sources showing Andromeda's satellites. You can really see the clustering.
Right. It color codes them by brightness and clearly marks satellites thought to be on-plane versus off-plane. The data highlights specific features, like a large cone about 101 degrees wide, containing 36 satellites.
That's a lot concentrated in one direction.
It is. And they also found hemispheres, one containing 32 satellites, another containing 29 that seems preferentially oriented towards the Milky Way. Statistical measures, like the geometric centroid and mean resultant length, quantify this lopsidedness. It looks real.
So how might QGD offer a different perspective here? Does repulsive gravity play a role again?
It could. Remember, in QGD, gravity is attractive, PDAX locally, holding Andromeda together, but it becomes repulsive, and gravity dominates beyond d lambda.
So maybe the gravity from structures outside the local group is pushing on these satellite galaxies.
That's a possibility worth exploring. The gravitational environment for a satellite galaxy isn't just Andromeda's pull, it's also potentially feeling a net repulsive push for more distant large-scale structures. This complex interplay of attraction towards Andromeda and repulsion from farther structures, all dictated by the QGD rules, could, over billions of years, shepherd these smaller galaxies into preferred alignments or planes.
A more complex gravitational landscape than just the pull of a dark matter halo.
Potentially, yes. It introduces large-scale environmental effects tied directly to the nature of gravity itself, which might explain asymmetries that are harder to account for in Lambda CDM where gravity is purely attractive.
Okay, QGD definitely paints a different picture. You mentioned it departs significantly from general relativity. What are some other key differences we might theoretically be able to test or observe?
There are several potential distinctions. We touched on gravity's behavior, but also the deflection of light. QGD predicts the same amount of deflection as GR, twice the old Newtonian value.
Which matches observation.
Yes, but the reason is different in QGD. It's not space-time curvature. It's described as an instantaneous change in the photon's momentum as it interacts with the gravitational field, the preonic field, of the massive object.
Instantaneous, that's a big one.
Huge. QGD posits that gravitational interactions mediated by ingravity are fundamentally instantaneous. No speed of light limit for gravity itself.
Wow, okay, what about other GR tests? Mercury's orbit.
QGD does offer an explanation for Mercury's perihelion precession, arguing it arises from correctly applying Newtonian gravity without an artificial time element. Getting the number to exactly match GR's prediction, though, requires more detailed theoretical work within QGD.
And things like quantum entanglement, non-locality.
QGD suggests these non-local quantum correlations might actually be a manifestation of these instantaneous gravitational interactions within the underlying preonic field, a direct causal link rather than spooky action at a distance.
So providing a physical mechanism for entanglement.
That's the idea. And gravitational waves are also different. Not ripples in space-time, but rather polarizations propagating through the preonic medium.
So fundamentally different views on gravity, light deflection, quantum mechanics, gravitational waves, and crucially, instantaneous gravity. That's a lot to unpack.
It's a complete paradigm shift, really.
Let's talk redshift. It's fundamental to how we measure cosmic disk lenses and expansion. How does QGD view redshift? Just the Doppler effect from expansion?
Not entirely. QGD proposes that a significant part of the redshift we observe, especially cosmological redshift, could be intrinsic.
Intrinsic, meaning generated at the source.
Yes, linked to the gravitational acceleration at the source. Light escaping a very strong gravitational field, like in a distant galaxy, might undergo an intrinsic redshift due to interactions within that intense preonic field.
So part of the redshift isn't due to distance or speed, but the environment where the light was created.
Correct. QGD suggests the observed redshift is likely a combination of this intrinsic gravitational redshift and any actual recessional velocity. It complicates the standard interpretation.
And there's another effect. You mentioned local reference sources.
Yeah, because gravity is instantaneous in QGD, a very distant, massive object could instantaneously exert a tiny gravitational influence on our local measurement standards, our reference light sources here on Earth or nearby. This effect would also need to be factored into redshift interpretation.
So the act of observing a distant galaxy gravitationally influences our measurement of its redshift. It's mind-bending.
It highlights how interconnected things become if gravity is truly instantaneous and tied to this preonic field.
So summing up, quantum geometry dynamics offers this really distinct alternative picture. Discrete space, these fundamental preons, push-pull gravity that flips repulsive at large scale.
Right, governed by p-gravity and in-gravity.
And we've seen how these core ideas might connect to real observations, the surprisingly fast growth of early galaxies, possibly explaining them via that self-amplifying gravity. The Dite Psi hints about evolving dark energy, which QGD could potentially explain as just repulsive in-gravity kicking in beyond lambda, maybe with lambda itself evolving.
A mechanism instead of a mysterious fluid.
And these odd lopsided satellite galaxy systems like Andromeda's, potentially sculpted by that complex interplay of local attraction and distant repulsion.
Offering a different take on galactic dynamics than pure dark matter halos.
Plus, these other radical ideas, instantaneous gravity, intrinsic redshift, it really changes how you'd interpret cosmological data.
It certainly provides a unique lens, yes. It's still a developing framework, obviously. It needs more quantitative predictions and tests.
Of course. But its appeal lies in trying to explain things from these first principles, these axioms, without needing to add extra ingredients like conventional dark matter or dark energy later on.
That's the goal of any fundamental theory, isn't it? Elegance and explanatory power from simple beginnings.
Absolutely. So for you, the learner, this deep dive hopefully gives a lot to think about. QGD presents this alternative path, potentially aligning with some perplexing observations. It definitely makes you wonder, doesn't it? What other cosmic mysteries, maybe inflation, maybe the matter-antimatter asymmetry, could QGD shed light on if we pushed it further?
And crucially, what experiments or observations could really put it to the test? Could we distinguish its prediction for light deflection, perhaps near the sun, from GR with enough precision? Or detect effects of instantaneous gravity somehow?
Big questions. The kind that arise when you seriously consider a universe that might be fundamentally discrete. Lots to ponder there.